Have you ever wondered what everything around us is made of? You see, the world as we know it is composed of building blocks so tiny they're invisible to the naked eye. These particles, called atoms, are the foundation of all matter. The idea of atoms has been around for thousands of years, but it was not until the early 19th century that the English chemist John Dalton proposed a comprehensive theory about these invisible particles. Dalton's atomic theory, as it's known, laid the groundwork for our modern understanding of atoms. His theory is based on several key postulates, the first being that elements, the purest substances, are composed of these indivisible particles called atoms. Each element, be it gold, oxygen, or carbon, is made up of its own unique type of atom. So, to simplify, every element is made up of tiny, indivisible particles called atoms, unique to that element. You might ask, are all atoms the same? Well, let's dive into that. As per Dalton's atomic theory, atoms of the same element are replicas of each other. They're like identical twins in the atomic world, having the same mass, size, and other properties. Think of it as a multitude of peas in a pod, each indistinguishable from the other. Now, while atoms of the same element are identical, atoms of different elements are unique. They differ in mass, size, and other properties. It's like comparing apples to oranges. Both are fruits, but they're fundamentally different in taste, color, and texture. The beauty of this concept is in its simplicity. Hydrogen atoms are all identical to each other, but different from oxygen atoms. And oxygen atoms are identical to each other, but different from hydrogen atoms. In essence, while all atoms share some common characteristics, they differ based on the element they represent. How do these atoms interact with each other? Here's where it gets interesting. John Dalton, in his atomic theory, proposed that atoms combine in specific whole number ratios to form compounds. What does this mean? Let's take the example of water. It's a compound, right? And it's always composed of 2 hydrogen atoms and 1 oxygen atom. This is a whole number ratio, 2 to 1. It's like a recipe. You always need 2 parts hydrogen and 1 part oxygen to make water. And this isn't just for water. This rule applies to all compounds. Whether it's carbon dioxide, ammonia, or table salt, they all follow this simple whole number ratio rule. So atoms don't just randomly stick together. They follow a precise recipe, a specific ratio to form compounds. It's a fascinating dance of particles, wouldn't you agree? In a nutshell, atoms don't just randomly combine. They follow a precise recipe to form compounds. What happens to atoms during a chemical reaction? Do they vanish or multiply? Well, let's dive into the last postulate of Dalton's atomic theory to find out. It's all about the rearrangement of atoms. You see, during a chemical reaction, atoms are not playing a magic disappearing act, nor are they multiplying like rabbits. Instead, they're more like dancers on a stage, changing partners to form new substances. It's a beautiful atomic ballet where atoms of one element disengage from their previous partners and form new bonds with atoms of another element. What's really fascinating is that throughout this dance, the total number of atoms remains constant. Atoms are neither created nor destroyed in the process. It's like a cosmic law of conservation, governing the world of atoms. So the next time you witness a chemical reaction, think of it as atoms swapping dance partners. Remember, in the world of atoms, nothing is lost, nothing is created, everything is transformed.